Good morning, dear students. Uh, this session, we will talk about the other approximate method. The other one is cantilever method. So, the last session, you might have got it very clear that the approximate methods are very simple to analyze a particular structural frame for lateral loads. Okay, so just recalling the portal method, whatever is done. So we started with the assumptions. uh, the two assumptions that are present in the portal method. The assumption one is to assume the point of contraflexures or no inflection points at the center of each member. That is the first one. Second assumption is very crucial for portal method. It decides the methodology. So it says, second assumption says, the column shear, which is interior column shear, is now twice that of exterior column shear. With that relation, we have started solving column shear first. Then we solve for column end moments as step 2. And then step 3, beam end moments. And then beam shear as step 4. And finally, column axial loads as step 5. So this was done in the last session, till the last session. So we comfortably, completed the portal method, which is half of your unit 2 syllabus. Okay. So going for the other method, which is cantilever method. Okay. So let me present that cantilever method. A little bit much understanding is required than portal method in this cantilever method, right? So let's see what is there. Right, this is step 5, where we solved for the frame in the last session. So I just brought in this step 5 just to remind you that a bit more easy way of transferring this direction of axial load from one half of the column to the other half of the column is, once you get the value of that particular column axial load, if you now draw it in the diagram, which means, like, for example, so you have solved for FAH value. Okay, so let me just go to that. So starting with no, you started with step 5 solving for FAH value. So you got this FAH. So what you do, you have the diagram with you. So place this arrow also, this one. Place this arrow also. So once you go to this joint H to solve, so what you have, a ready-made notation is already there and a value. Okay, so when you deal with joint H, let's go to that. You see here. Giant H, when you see, you see there is ready-made uh, arrow is already readily available, which is now brought in from the diagram itself. That is what is the easy way of doing it. Okay, so this arrow is as it is transferred, okay, into that diagram, half of this. So upward arrow to the right, uh, upward arrow above joint H, and below that this value you are going to solve. You don't know this value and the nature. So when you take joint H, this is what I mean. See here, right hand side upward arrow above the joint, and this you are going to solve HI, and that is 23.34 HI. So once you solve for any column axial load, just put it in the diagram with the counterpart of that. I mean to say other half of the column also you mention the nature. So once you go for the next joint, and you don't have to worry about which direction it is, because it is already there in the diagram placed already. This is what is the easy way of getting the axial load onto the free body diagram. That's what I just wanted to give you one more tip uh, to to easily guess the direction of column axial load when you take the other half of the column from the connecting joint. Okay, right. So let's see cantilever method. So again, the cantilever method is also is the method used for approximate solution, approximate analysis of uh, frames, structural frames applied by lateral loads only, right? Right. Again, there are two assumptions here, as you see. Inflection points occur midpoint of each member, nothing but point of contraflexure, or nothing but zero bending moment location. Right, that is common, as I said in the initial point of time, that for both the methods, either portal or cantilever, first assumption is same. So it differs only with the second assumption. So what is that? Right, you clearly observe here, axial stress intensity, axial stress value in a column is proportional to its horizontal distance from CG of all the columns in that particular story. Okay, let's see what it is. Say this is a particular frame. Okay, all right, consisting of some columns. Okay, so right. Okay, so what it said, CG of all the columns. Okay, so you have 3, 4, 5 columns here. Let us imagine that the CG of all these columns is here. Okay, of these 5 columns, center of gravity is here. Okay, right. So if this is the CG location, what it is telling, axial stress in a column is proportional to, say, this is C1. What is axial stress? Sigma C1. Axial stress in column 1 is proportional to, Let us say this distance is x1 proportional to x1. This is how it is. Right, horizontal distance from the CG. Okay, axial stress in this particular column, column 1. So axial stress is proportional to its distance from CG of all those columns. So in a simple manner, I write it like sigma is proportional to x, sigma of column. So axial stress in a column is proportional to its distance from CG of all the columns in that particular story. So you take any column in a particular floor or a story. Okay, find CG of all those columns. Okay, then the axial stress in a particular column is proportional to its distance from CG of all the columns. This is the assumption 2. Right. So by this you should be knowing that we are working with column axial stress means what? Column axial stress means what? Column axial load by cross sectional area is proportional to its distance. So what you will be solving first? Column axial loads you will be solving first, because your assumption is on column axial loads. Okay, so when you just recall portal method, when did you calculate column axial load? It is the last step. We started with column shear. Got it? So now you are starting with column axial loads you are starting with. So once you know column axial load, what is the connecting quantity what you are able to calculate is what? Beam shear. Okay, once you know, just reverse it. You think in a reverse manner. There in portal method, you know column beam shear. From beam shear, you have calculated column axial load. Now it is reverse here. You know column axial load first. You are going to get all column axial loads first. Then very next step is to calculate a beam shear. Once you know beam shear, you are going to calculate beam end moment. Once you know beam end moment, you are going to calculate column end moment. Once you know column end moment, you are going to calculate column shear. This is the flow of steps. Anyhow, we will be discussing them. Right. So this is how the cantilever method is now to be proceed to solve for the solution, approximate solution. Right. So let's see what is there in the introductory part. Okay, so the assumption is told, and why, or how you can relate that assumption with the theory available. Okay, so this is how it is, right? So imagine that the total frame is a cantilever. Okay, so that is shown here. Cantilever, this is a cantilever beam. It is not actually just a vertical member. It is a frame consisting of so many columns. Let us imagine that. Okay, in such column, the bending stress, because you are having lateral loads on the building frame. Okay, so you have a lateral load. Because of that, the column is going to bend. Okay, so depending on the load that is applied. So if it is of right hand side, you applied the load, so the bending is going to be like this. Okay, right. So if the load is towards left hand side, the bending is towards the left, right. This is going to be bending nature. So bending will be there, so bending stress will develop. And how the bending stress is, so you just recall your bending chapter, sigma m by I, okay, f by y, all that. Okay, so bending stress, how you draw across the cross section, how you draw bending stress is by neutral axis 0 and topmost fiber. If you remember, if you take a cross section, how you draw bending stress is a cross section of the beam. So how you draw this is like this, right? Got it? So here the bending stress is drawn both positive and negative on the same side of this axis. Okay, but showing the arrow downward and upward for the natures here. So for compression it is shown upward, for tension it is shown downwards. So tension this face, and mean to say this is tension side, compression side. Okay, so you observe these two triangles here. This triangle is, compression triangle. This tensile. Okay, here also you have two triangles, but one on the other side, the other on this left side, right? So on the either side of the reference line, but here on the same side of reference line, here also you can follow that same side of reference line and notating that this is some tension, this is some compression, like that also can be done, right? But this is general nature of drawing this for beams, and for columns we follow this way, right? Got it? So now what is? So second assumption you can understand with the help of the concept that is said like this. So if you assume the entire frame as a cantilever column, the column will be treated as vertical fibers. Bending stress at a cross section will become axial stress in the fibers. So how axial stress is proportional to the distance, you may be surprised. This is the concept that is being adopted. Okay, so how it is being adopted, let's see. uh, the concept the told here, the concept that is now is told here is like this. Okay, let's go back to that. So how is look like this. Right, so second assumption is telling you that uh, the column axial stress, so axial stress in column, imagine that this line is a column in the frame. Imagine this is a building frame and this line is a column. Okay, so what you have on this line, there is some stress acting here. You see that this line, this, okay, let me just go with a different color. So this is now stress acting on that line. So if you treat that as a line, the stress now it will become axial force, right? So whatever it is. So this if you imagine that there is one more column here, just imagine. Okay, and you see the stress is only this much, and if this is the column, the stress is this much. So how the stress is varying, you see, 0 at neutral axis, and it is proportional. You see this is a straight line, inclined straight line, right? So what does that mean? Y equal to mx line. Just a second. So y equal to mx. So y is proportional to x. Okay, so the stress is proportional to the distance. So sigma here, stress is proportional to x. This is how that concept is being taken. So treating the entire frame, say this is some building frame having some columns. Okay. So imagine this entire frame as just a cantilever. Okay, something like this. A solid cantilever, something like this. So now this is a cantilever. So all the loads that are being acting here on the frame, just have those loads also on this cantilever. But this is the concept. If this is the neutral axis, right? So this is the neutral axis that is present, right? This is frame and assumed cantilever. Okay. So just like how bending stress is proportional to the distance from neutral axis, the same concept is adopted here. Column axial stress. Okay, so here for the cantilever it is bending stress, but for that column, for say that the line is a column, right? So for that it is like axial stress. So sigma. If you just take one slice of that cantilever, one slice, okay, so that is that will become axial stress, because that is acting along that axis of that column slice. Okay, infinitely small piece, right? So bending stress for the total frame is becoming axial stress for column. Okay, because it is like a fiber in the cantilever. Okay, it is like a fiber, the one layer. Okay, column is like a one layer in that cantilever. So this is the information behind that second assumption, how the second assumption is taken. It's like now portal method also we have explained why that second assumption has come. Okay, so portals, the entire frame can be split into independent portals, simple portals. So overlapping those portals, you have two columns at interior column location. So imagining that the columns will take equal no, shear. So the interior column will have double the shear than the exterior column. That's how it is explained. Same here in cantilever method also. The concept behind that is like assuming a frame as a cantilever. Okay, a cantilever beam, right? So bending stress in the beam is now formulated as axial stress for a particular layer, okay, or a fiber. So that layer is nothing but a column. So if you take one small section here, a part of just dx, that is nothing but a column in the frame. That's how it is. Okay, right? That is the concept behind that. Anyhow, the procedure is already told just now, and once again we will just go for it. So we start calculating first column axial loads, because your assumption is on column axial loads. Okay, so we calculate column axial loads first. So before that, what you need, you have to locate CG of all the columns, then apply second assumption. You will have some relation between column axial loads of columns of that particular story, then solve for axial loads. Anyhow, we will take up one example. You will see how we calculate CG of all the columns, and how we apply assumption to, and how we calculate axial loads. Right. Okay. Right. Once you get column axial loads, we are going to calculate beam shear, connecting quantity. Once you know beam shear, the force into the distance is beam end moment. So once you know beam end moment, if you take the joint, you will get column end moment. That is the next step of calculation, column end moment. So once you know column end moment, column shear can be calculated with the relation between force into distance. Okay, that's column shear. So only step one you have to practice a bit much, with much care. Remaining all are just multiplications or divisions like that. Okay, so this is the flow of the procedure, right? So when we take an example, we solve step by step, then you will know better than this, right? Thank you.